Good afternoon. Today we are going to learn about the preparations and properties of organic compounds containing nitrogen. Okay, so the plan for the lecture today will be, next slide. We'll start with the introduction and the classification of the nitrogen containing compounds. Then we will go on to their structure. Okay, then we will do the preparations and properties of amines, and then the preparations and properties of diazonium salts, and finally we will go on to the question. Next slide. If you look at amines they are formed by systematically replacing one or more hydrogens in ammonia by an alkyl or aryl group. Depending upon number of hydrogens that are replaced, the amines are classified into primary, secondary and tertiary amines. So when one of the hydrogens is replaced by the alkyl or the aryl group, you get the primary amines. When two hydrogens are replaced, you will get a secondary amine, and when all the three hydrogens are replaced, you will get tertiary amine. There is another class of amines that you get from the ammonium salts. So if you replace all the four hydrogens of the ammonium salt by the alkyl group, you will get a quaternary ammonium salt. Now, like ammonia, all these derivatives of ammonia, that is amines, they will also have a lone pair of electrons, because of which they will exhibit basic character and also will be nucleophilic in nature. Correct? As far as their occurrence is concerned in nature, they are widely found in both plants as well as in the animals. Next slide. This classification we have discussed. If you look at the bottom, you see the first compound. This is an example of a primary amine here. This is a primary amine. One of the hydrogens on nitrogen being replaced. This is a tertiary butylamine. Correct? This is another example of a secondary amine. This compound is commonly known as piperidine. Okay? This is an example of a tertiary amine. You can see all the three hydrogens have been replaced by alkyl or aryl group. This compound will be called N,N-dimethyl aniline. Okay? And this is an example of a quaternary ammonium salt. As I said, when all the four hydrogens on the ammonium ion are replaced by alkyl group, you get the quaternary ammonium salt. Correct? Next slide. Now, amines, they are also classified depending upon the nature of the hydrocarbon unit that is present. They can be aliphatic amines. When nitrogen is attached to an aliphatic carbon unit, they are aliphatic amines. Like you have this is aminomethane. Okay? Aminoethane, nitrogen is attached to an aliphatic carbon. So they are aliphatic amines. When nitrogen is attached to an aromatic carbon, they are called aromatic amines. This compound is aniline. Okay? There is a third class of amines. They are called aryl alkyl amine. For example, this compound is benzyl amine. You can see there is an aromatic ring here, but the nitrogen is not directly attached to the ring. So this is an example of an aryl alkyl amine. Okay? And there is a fourth class of amine that I have displayed here. They are called heterocyclic amines. The word hetero means different. Different. You have come across carbocyclic compounds, cyclic compounds where all the corners of the cyclic structure are occupied by carbon. Now, if you have compounds where one or more carbon in the cyclic structure are replaced by atoms other than carbon, For example, it can be nitrogen, it can be sulfur, it can be oxygen. Those compounds are called heterocyclic compounds. So these are some of the examples of heterocyclic amines that you come across. This is pyridine, this is pyrrole, this is piperidine that we talked about. Okay, some examples of heterocyclic amines. Let us look at, you have done nomenclature at length in detail. Just to give you common names of some of the amines. If you look at this compound, this will be called, because there are two phenyl rings, diphenylamine. If you look at this compound, this will be cyclopentyl methylamine. Likewise, diethyl methylamine, and so on. These are some of the examples of amines with their common names that I have given for you. Next slide. Now, as I said that amines, they are found widely in the plant as well as in the animal system. As far as their applications go, you find large variety of applications of these compounds containing nitrogen. For example, the first example is in dyes. Have you heard of methyl orange? Methyl orange is an acid-base indicator which is used in the acid-base titrations. Okay? That is an amine derivative. Second is, there are neurotransmitters. For example, adrenaline, if you have heard of, which is used to increase the blood pressure in the body. And there is one more compound called serotonin. Serotonin imbalance in the body is responsible for a condition called schizophrenia. Have you heard of schizophrenia? Double personality. It is because of imbalance in this compound serotonin, which is again a nitrogen derivative. Okay? Then proteins. Proteins that you found in body, they are made up of nothing but amino acids. Again, derivatives of nitrogen compounds. Okay? And finally, many of the drugs that we take are also derivatives of nitrogen. Some examples I have listed for you here: morphine, nicotine, and also caffeine, which you find in tea, is also a derivative of nitrogen. Okay? So you see, so many of them find use in daily life around us. This compound, nylon, we all know, again obtained from nitrogen containing compounds. Quaternary ammonium salts, they are used as detergents, and also they are used as fabric softeners in liquid detergents. The fluffiness of your woolens is because of the presence of these quaternary ammonium salts, which act as fabric softeners. Okay? And this one last compound which you find in your shampoos, glycine betaine, this is called. This is used for strengthening of your hair. This is a constituent of your hair shampoos. Okay? So many examples we have seen of how nitrogen compounds, they are present around us and how they are helping us. Okay? Next slide. Now we come to their structure and the bonding. Now, if you look at the structure of ammonia, you have already learned. You know that nitrogen in ammonia is sp3 hybridized. Likewise, amines also, the nitrogen will be sp3 hybridized. Now, sp3 hybridized nitrogen means the geometry should be tetrahedral. Tetrahedral geometry with bond angle 109 degree 28 minutes. However, what you find in case of amines is that amines do not have a typical tetrahedral geometry. They have a geometry that we call pyramidal geometry. They have a pyramidal shape, distorted tetrahedral. Okay? Why that happens? Now, if you can see here, let me write the structure of an amine. This is aminomethane. If you look at this compound here, you have methyl group here and two hydrogens, and the fourth corner of the tetrahedron being occupied by nitrogen, the lone pair of electron. Now what happens is there are repulsions between the lone pair and the bond pair. Because the lone pair bond pair repulsions, they are stronger than the bond pair repulsions, what you find that the bond angle shrinks. The bond angle shrinks from 109 degree 28 minutes to about 107 degree in primary and in the secondary amines. Okay? But when you go to tertiary amines, what happens is all the three hydrogens will be replaced by the alkyl or aryl group. Okay, so you have three bigger groups surrounding nitrogen. So there are mutual repulsions. Because of repulsions, the bond angle slightly expands to 108 degree instead of 107 degree. So tertiary amines, the bond angle is 108 degree in place of 107 degree. Okay? And the geometry is pyramidal. Is that okay? This I have already explained to you. Ammonia, bond angle 107 degree, and in tertiary amine, why it expands to 108 degree. Next slide. Okay. Now, you have learnt that if you have a carbon compound where all the four groups which are attached to carbon, they are different, then that compound is chiral, and it can exist as a pair of enantiomers. It is optically active and it can exist as a pair of enantiomers, right? Now if you look at a nitrogen compound that I am going to draw here now, you look at this compound here, what you find here is, this is a secondary amine, correct? There are three different groups attached to nitrogen and the fourth is lone pair of electrons. So all the four groups are different. If all the four groups are different, you expect, like in case of carbon compounds, the nitrogen compound also to be chiral. Okay? If it is chiral, it should exhibit a pair of enantiomers. It should exist as a pair of enantiomers. But what you find is that these enantiomers are not isolable. They cannot be isolated. This happens because of a phenomena that is called pyramidal inversion. Let us see what is that and what makes a compound containing, a chiral center optically inactive. I said the phenomena is called pyramidal inversion. Now what happens is, because nitrogen has lone pair of electron, the hybridization here is sp3, but it is capable of going from an sp3 hybridization to an sp2 hybridization to attain a planar geometry. Okay, that is a planar geometry that it gets. Now from here it can again go back to sp3 hybridization, you can see 1, खुला नहीं हुआ है, वो सील्ड है, इसको खोल के 1 and 2, they are mirror images. But what you find here is, at room temperature, this flipping from this form to this form requires energy of the order of only 25 kilojoules per mole. Now this much of energy is easily available at room temperature. So at room temperature, this molecule flips from this orientation to this orientation and vice versa. Because of which what happens is you are not able to isolate the enantiomers, and the two enantiomers are not isolable in spite of the fact that nitrogen is having 4 different groups attached to it. Okay? And this phenomena, as I said, is called pyramidal inversion. Okay? Next slide. So I've already explained to you, you can see here how it has gone from this geometry to the planar form and then to the other enantiomer. Okay? Next slide. Now, the important thing that you have to remember here is, as long as nitrogen has lone pair of electrons, this flipping from sp3 to sp2 and then from sp2 to sp3 will be facilitated. However, if nitrogen does not have lone pair of electron, and that will happen in case of quaternary ammonium salt, when nitrogen donates its lone pair of electron to form the quaternary ammonium salt. So in quaternary ammonium salt, the lone pair of electron is no longer available on nitrogen. So when lone pair of electron is no longer available, this sp3 sp2 flip cannot take place. So quaternary ammonium salts will be optically active, and the two enantiomers can be isolated because there is no pyramidal inversion occurring in that case. Is that okay? So this example I have shown you here, the two enantiomers, they can be easily isolated because it is a quaternary ammonium salt. So no lone pair of electrons available, no pyramidal inversion taking place. Okay? आधी छाया आ रही है इसके ऊपर ना, वो अगर उसको बंद कर देंगे तो शायद बच्चों को ठीक से दिखना नहीं होगा, शायद ठीक से नहीं दिख रहा ना, वो आधी रोशनी आ रही है ना. हाँ. नेक्स्ट स्लाइड चेंज कर दो. मेरे को दे दो पानी मेरे लिए. Next, let us come to their physical properties. Boiling point. Now amines, because they are polar compound, there is electronegativity difference. If you see the electronegativity of nitrogen, oxygen and hydrogen, it follows this order. So the electronegativity difference between oxygen and hydrogen is about 1.4, and the electronegativity difference between nitrogen and hydrogen is about 0.9. So you can see that the nitrogen-hydrogen bond is less polar as compared to the oxygen-hydrogen bond, which is more polar than the nitrogen-hydrogen bond. So you expect that the boiling points of amines will be lower than those of corresponding alcohols having comparable molar masses. Number one. Number two, when you compare amongst amines, you will find that the order will be primary, greater than secondary, greater than tertiary. What is the reason for that? If you look at primary amine, what you find is that it has 2 hydrogen bond donor sites and it has 1 hydrogen bond acceptor site. ठीक है? So a primary amine can form stronger hydrogen bonds when you compare it with a secondary amine, which has one hydrogen bond donor site and one hydrogen bond acceptor site. When you come to tertiary amine, there is no hydrogen bond donor site. You have only one hydrogen bond acceptor site. So the strength of the hydrogen bonding will decrease as you go from primary to secondary to tertiary. So the order of boiling point will be primary, then secondary, and then tertiary. Correct? Next slide. Now, this I have already explained to you. Next slide. Solubility. Again, solubility of amines, you find the aliphatic amines up to carbon number 6. They are soluble in water. Beyond that, the solubility is practically negligible. The solubility is again because of the tendency of amines to hydrogen bond with water molecules. When you look at an amine, like amines can form hydrogen bonds amongst themselves, they can also form hydrogen bonds with water, right? Like this, correct? So the number of hydrogen bonding sites which are available on primary amine again will be more than the number of hydrogen bonding sites which are available on a secondary amine and then on a tertiary amine. So the extent of hydrogen bonding with water again will decrease as you go from primary to secondary to tertiary. So that means as the branching increases, the extent of solvation of the amines will decrease. So as a result, the solubility will go down. Okay? And importantly, aromatic amines, because of the presence of large hydrocarbon part, they will be insoluble in water. They will largely dissolve in non-polar solvents like benzene. Okay? Next. If you look at primary amine here, there are two hydrogens attached to it. Okay? When you dissolve it in water, it can form hydrogen bonds with water molecule. But when you go to tertiary amines, there are no hydrogens attached to nitrogen. So it cannot form hydrogen bonds with water molecule. That is why tertiary amines will not be soluble in water. Is that okay? So as I have shown here, you can see here, in case of tertiary amines, there are no hydrogen bond donors. There is only a hydrogen bond acceptor. So the extent of hydrogen bonding of tertiary amine is minimum. That is why their solubilities are the lowest. Correct? Next slide. The next is the basicity of amines. Now, if you compare the basicity of amines with water or with ammonia, what you find that amines are stronger bases than both water as well as ammonia. Okay? So when you dissolve amine in water, it will take up a proton from water and it will ionize. To form this. Correct? The ammonium ion will be formed. Now, the presence of hydroxide ion can be established by adding either aluminium chloride or by adding ferric chloride. If you add aluminium chloride, you will get white precipitate of aluminium hydroxide, or if you add ferric chloride, you will get a brown precipitate of ferric hydroxide, which confirms the presence of hydroxide ions in the aqueous solution of primary amines. ठीक है? This I have already explained. Next slide. Now, if you look at the order of basicity of aliphatic amines, I have given you in this table. Look at the pKb values. The basicity of amines will be given by the pKb values. Lower is the value of pKb, stronger is the base. ठीक है? You find in case of aliphatic amines, the pKb values normally lie between 3 to 4.22 for aliphatic amines. For aromatic amines, the values lie between 8 to around 9.5. So, if you see, the order of basicity of amines will be like aliphatic, stronger than ammonia, which will be stronger than the aromatic amines. That will be the order of basicity, because ammonia, the pKb value is 4.74. Basicity will increase. It will be reverse. Acidity is given by the pKa values, lower value of pKa or higher value of pKb. See, if you see, pKa plus pKb is 14. If pKb is low, pKa will be higher. ठीक है? Next slide. So, this is the as I said, pKb values of some of the aromatic amines, and I said that they lie between the values of 8 to 9.5. Okay? Next slide. Let us now consider the factors which affect the basicity of amines. I have listed 5 factors here. There are in fact 6 factors which affect the basicity of amines. Let us see these factors. The first is inductive effect. The second is hybridization of nitrogen. The third is solvation. The fourth is steric effect to solvation. We will take specific examples and understand what does steric effect to solvation mean. Next is resonance. This will come into play in case of aromatic amines. And the last point is steric inhibition to resonance. Again comes into play in case of aromatic amines. So, these are the 6 factors which affect the basicity of an amine. ठीक है? We will take up these factors one by one. The first factor is hybridization. Now, if you look at hybridization, when the hybridization of nitrogen changes from sp3 to sp2 to sp, the percentage S character has gone from here 25% from here to 50% here. ठीक है? As the S character increases, the lone pair of electrons will be strongly held. Okay? So, the basic character will decrease. So, the basic character decreases as the hybridization on nitrogen increases from or changes from sp3 to sp. If you see the example here, this compound is pyridine, nitrogen is sp2 hybridized, the pKb value is 8.75. You come to this compound piperidine, hybridization on nitrogen is sp3. Okay? The pKb value you can see 2.88. So, piperidine is a much stronger base than pyridine, because piperidine, the hybridization on nitrogen is sp3, and in case of pyridine the hybridization is sp2. ठीक है? That is the first point. The next is resonance. As I said, resonance comes into play in case of aromatic compounds. We will study this in detail when we come to aromatic compounds. Just to tell you here that if you compare aminomethane with aniline, you find that aminomethane is a much stronger base than aniline, and that is happening because of resonance effect which comes into play in case of aromatic amines. What happens here is this lone pair of electron, because of the minus R effect of benzene ring, gets delocalized onto the ring. ये तो उसकी ये बात है, पेन बीच में चाहे So if you look at this resonance structure, what is happening is the lone pair of electron on nitrogen has got delocalized and nitrogen has acquired a positive charge. That decreases the basic character of aromatic amines. There are in fact three reasons for decreased basicity of aromatic amines as compared to aliphatic amines. The first factor is resonance, as we have learnt here. The second factor is this nitrogen is attached to an sp2 hybridized carbon. The sp2 hybridized carbon is more electronegative, so it withdraws electrons from nitrogen towards itself, which decreases the basic character here. What is the hybridization on this carbon? It is sp3. So an sp3 hybridized carbon is less electronegative as compared to an sp2 hybridized carbon. So decreased basicity because of the higher electronegativity of this sp2 hybridized carbon. Number 3, if you see the stability of the conjugate acid, what will be the conjugate acid formed? Anilinium cation. Now, how many resonance structures will you be able to write for anilinium cation? Only 2. If you look at aniline, you can write 5 resonance structures for aniline, and if you look at anilinium cation, there are only 2 resonance structures possible. So the conjugate acid is less stable as compared to aniline. That is why the decreased basic character. So these 3 reasons are responsible for the decreased basicity of aromatic amines as compared to an aliphatic amine. Is that okay? Next slide. Let us come to inductive effect. Now if I take ammonia and if I take methylamine and if I take ethylamine, ammonia, nitrogen has 3 hydrogens attached to it. When you come to methylamine, it has 1 methyl group which offers plus I. Okay? When methyl is replaced by ethyl, it has a stronger plus I effect. So you find that basicity increases as you go from ammonia to methylamine to ethylamine. That means unka pKb value will go on decreasing. Correct? But if you look at this order here, what do you find? Ethylamine, then propylamine, then methylamine, and then ammonia. If we are saying that inductive effect is responsible for the increased basicity, then propylamine should have been a stronger base than ethylamine, but that is not the case. That means there is something other than inductive effect which is also coming into play, which is responsible for the basic character. We will learn it a little later here. Okay, let us keep this in mind. We will come back when we discuss this here. Next example, if you see methylamine then benzylamine, and then ammonia. If you see, this is methylamine, आगे आ जाओ, यहाँ से साफ दिखेगा. मिथाइलामीन, मिथाइल ग्रुप हैज अ प्लस आई इफेक्ट. यहाँ पे दिख रहा है आपको साफ? आर यू एबल टू सी? वहाँ पे नहीं दिख रहा, आप इधर आ जाओ. बेंजाइलामीन में क्या होता है? Now CH2 is attached to a phenyl ring. A phenyl ring offers minus I effect. So the net activation of nitrogen, increase in the electron charge density on nitrogen, is more in case of methyl than in case of benzyl group because of minus I effect of the phenyl ring here. So the order is methylamine, then benzylamine, and then ammonia. Okay? So you have understood how inductive effect increases the basic character of aliphatic amines. Correct? Next we come to solvation effect. The other factor which is important deciding the basicity of amines is solvation. Where, as I said, when you put an amine in water, what will happen? It takes up a proton and it forms the conjugate acid. Okay? For example, if you have a primary amine, when you put this in water, it will exist in this form. The cation will be this, and this will be extensively solvated by hydrogen bonding to water molecules. Correct? Now, in case of a primary amine, the nitrogen will have 3 hydrogens attached to it forming hydrogen bond. In case of secondary amines, you will have 2 hydrogens. In case of tertiary amines, you will have only 1 hydrogen. So what is happening is the extent of solvation will go on decreasing as you go from primary to secondary to tertiary. Okay? So the higher the solvation, higher is the stability. So based on solvation, the stability of the conjugate acid will follow the order primary, then secondary, and then tertiary. And based on inductive effect, the order should have been this. So the actual order of basicity of amines, aliphatic amines in solution is a resultant of these two factors. This is coming because of solvation, this is coming because of inductive effect. So the net order that you find is in case of methylamines, you find the order is secondary, primary, tertiary, and ammonia. In case of higher aliphatic amines, the order is normally secondary, tertiary, primary, and ammonia. Why this difference comes in case of methylamine is because the methyl group is small in size. Because it is small in size, it gets extensively solvated. So in case of methylamines, solvation is a predominant factor over inductive effect. And because of extensive solvation of primary amine, the primary amine becomes more basic than tertiary amine. Okay? In case of higher amine, the size of the alkyl group is bigger. So inductive effect is a predominant factor over solvation. That is why tertiary amine will be a stronger base than primary. But in both cases, the secondary amine is most basic. So that is the order of basicity of aliphatic amines. So now you understand steric inhibition to solvation. Bigger alkyl group prevents the solvation of the conjugate acid. The stabilization decreases. That is why in case of propylamine, because the size of the alkyl group is bigger, there is steric inhibition to solvation. That becomes an important factor over inductive effect. That is why the order of basicity is ethyl, then propyl, then methyl, and then ammonia. Have you got my point? Next slide. So this I have already explained to you, inductive effect. Next slide. In case of aromatic amines, we have learned that there are three factors: resonance, sp2 hybridized carbon, and decreased stability of conjugate acid, which are responsible for decreased basicity of aromatic amines. What we will now learn is what is the effect of substituents on the basicity of amines. Okay? Next slide. Now if you see here, if you have an electron donating group attached to the ring, stronger the electron donating group attached to the ring, higher will be the basic character. The pKa values are increasing, so pKb values are decreasing, so the basic character is increasing. Likewise, as you go from here, as the electron withdrawing group strength increases, the basic character will go on decreasing. Okay? So an electron withdrawing group will decrease the basic character of aromatic amines, and electron donating group will increase the basic character of aromatic amines. Is that okay? Now we will see the trends in the next slide. There is one rule that you have to always remember. When you compare the basicity of an ortho-substituted amine and that of a para-substituted amine, irrespective of the nature of the group, whether G is electron donating or electron withdrawing, you will find that ortho-substituted amines are weaker bases than para-substituted amines, and this is attributed to something that we call ortho effect. This ortho effect is a combination of steric effect and electronic effect, and when I take up specific examples, I will explain how ortho effect is leading to a decreased basicity of ortho substituted amines. Okay? Okay? Yeah. Let us come to specific example where the donor is OCH3. When the donor is OCH3, if you can see the order here, it is, this compound is called anisidine. Common name is anisidine. This is para anisidine, stronger base than aniline, then ortho, and then meta. Let us understand why this order. If you can see here, when you have OCH3 group, okay, OCH3 group donates electrons by plus R effect, but it withdraws electrons by minus I effect. Correct? This plus R effect can operate only at ortho and para positions. Right? At meta position, there is no resonance. So at meta position, what will happen? OCH3 will be withdrawing electrons. So meta substituted compound will be least basic. So that explains why it comes in the end. Okay? Now, between ortho and para, this is para and this is ortho. You have plus R and minus I operating at both the cases, but you have something called ortho effect here. What is ortho effect? Number one, what happens is when the protonation takes place, there is steric inhibition to solvation. Again, when you have a bulky group adjacent to NH2 group, the protonation will take place, and what will this become? This will become NH3 plus, and then it will get solvated. Now, the presence of this bulky group here prevents the solvation of this conjugate acid. So it is decreasing the stability of conjugate acid. That is ortho effect. Number one. Number two, when you have bulky group present here, see, in a free base you have nitrogen being surrounded by 2 hydrogens. Okay. But when it gets protonated, the conjugate acid will have 3 hydrogens attached to it. So crowding is increasing. Again, because of steric factor, the conjugate acid will be less stable than the conjugate acid formed in this case, because there is no steric interaction here. That is why para substituted compound will be more basic than the ortho substituted compound. And it is this ortho effect which is making orthoanicidine less basic than aniline. Okay? So that explains the order: para, then aniline, then ortho, and then meta. Any doubt? Next slide. Next, let us come to hydroxyl group. Now, OH is also an electron donating group. Both plus R and minus I is operating in case of OH also. So you expect the same order should have been para, then aniline, then ortho, and then meta. But what you find here? You find that in case of para-aminophenol, this is the para-aminophenol, aminophenols, para, then ortho, then aniline, and then meta. Meta explained because minus I effect, so least basic, correct? Now what has happened here? That has increased the basicity of ortho substituent despite ortho effect. We said ortho effect hai, because of which the basicity is less. Now, but what happens in case of orthoaminophenol is that the conjugate acid is stabilized by hydrogen bonding, intramolecular hydrogen bond. It is this intramolecular hydrogen bond formation which is taking place in ortho-substituted aniline, which increases the basicity of orthoaminophenol as compared to aniline. Okay. Intramolecular hydrogen bond. Next slide. Now let us come to aryl alkyl amine. See, nitrogen here is directly attached to ring. So lone pair of electron get delocalized onto the ring, decreased basicity. Here nitrogen is not directly attached to the ring. The benzene ring is only offering minus I. There is no minus R. Definitely benzylamine will be a stronger base than aniline. Correct? Let us come to basicity of N substituted aniline. When the hydrogen on aniline amino group is replaced by an alkyl group, you find that the basic character follows the order tertiary, then secondary, and then primary. You can see here NN dimethyl aniline, then N-methyl aniline, and then aniline. Now there are two reasons for this. The first you can understand is inductive effect. Okay? When you have two methyl groups attached to nitrogen, inductive effect, the electron charge density on nitrogen is high, because of which the basic character will be more. But this is not the only factor which increases the basicity of this amine. The second factor is, as I said, steric inhibition to resonance. What happens is when you have two alkyl groups here, this nitrogen is no longer in the same plane as this carbon. Now for resonance to take place, this nitrogen and this carbon should be in the same plane. Because of these two alkyl groups, the nitrogen and carbon are no longer in the same plane, so the lone pair of electron on nitrogen cannot get delocalized onto the ring. So the more important factor for increased basicity of dimethylamine is steric inhibition to resonance and not inductive effect. Inductive effect is an important factor, but more important is steric inhibition to resonance. That is by the order dimethylanilene, then N-methylaniline, and then aniline. Is that okay? But when the hydrogen is replaced by an aryl group, you find that the basicity reverses. Aniline, then N-phenylaniline, and then NN-diphenylaniline. Can you understand why that is happening? And that happens because this is aniline. From aniline, when you go to N-phenylaniline, you have two benzene rings. Two benzene rings offering minus R effect. Okay? And when you go to diphenylaniline, there will be three benzene rings. So the stability of the conjugate acid will reduce as you go from aniline to N-phenylaniline to NN-diphenylaniline. So what is an important factor here? The important factor here is the stability of the conjugate acid. Okay? Because of the minus R effect of the two attached benzene rings, the basic character will be lowest here and highest here. Is that okay? हो गया? चले आगे? Next slide. Now methods of preparations of amines. There are 7 methods of preparation. The first is Hofmann ammonolysis. Then we will do alkylation of azides. Then nitryl, isonitrile, amide, oxime reduction. Next will be phthalimide synthesis. Next is phthalimide synthesis. This one. Next will be reductive amination, where you can convert carbonyl compound to amine having same number of carbons. Next is Hofmann degradation, where you will be able to convert an acid or an amide to an amine having one carbon less. And finally Schmidt reaction, where again you can convert a carboxylic acid to an amine having one carbon less. Is that okay? Next slide. Now first is Hofmann ammonolysis. I am sure you have learned that Hofmann ammonolysis is not a very good method to prepare amines, because you have a mixture of products being formed. What happens is, if you have say ethyl bromide reacting with ammonia, the first product, of course the reaction follows SN2 mechanism, nucleophilic substitution reaction taking place, you will get ethylamine formed here. But the reaction will not stop here. It will further react with ethyl bromide. You will get diethylamine, which will further react with 2 more molecules, and the final product here will be the quaternary ammonium salt. So if you want to prepare primary amine, along with that you will get a secondary amine also being formed, and you will get a tertiary amine also being formed along with the quaternary ammonium salt. You can control the percentage of these products. For example, if I want a primary amine, then what I can do is I can use ammonia in excess, 1:10 mole ratio. If I take, then I will get primary amine as the major product, but again mixtures will still be there. If I want quaternary ammonium salt, I can start with excess of alkyl halide. I will get this as the major product, but again mixtures remain. So it is not a very good method to prepare amines from alkyl halide. A better method to convert an alkyl halide to a corresponding amine is the next method, where we are converting alkyl halides to amines via azide. So what you do is you take ethyl bromide here, react it with sodium azide or potassium azide, ठीक है, and prepare the corresponding azide. ठीक है. Azides, unlike amines, are not nucleophilic. Amines are nucleophilic, that is why polysubstitution is taking place. Azides are not nucleophilic, so no polysubstitution reaction takes place. This azide, you can reduce it with H2 nickel or with LaH, lithium aluminum hydride, and you can get the corresponding amine. So you can see, if you have to prepare a primary amine, a better way to convert an alkyl halide to an amine is via the azide route, where you will get exclusively primary amine as the product. Okay? So I have written here, the overall reaction is conversion of alkyl halide to corresponding amine. That is important, corresponding amine. Okay? Next slide. If I take the example of these tertiary amines, trimethylamine, triethylamine, tri-N-propylamine, inductive effect is increasing as you are going from top to bottom. The basic character should have increased as you go from top to bottom. But what you find is the order is actually you can see here the steric effect because of the bulkier alkyl group. The basic character of tripropylamine is less than the basic character of triethylamine. The reason is not just, number one, because of the bigger alkyl group, there is steric inhibition to solvation. Number one. The second factor is because of bulky alkyl groups. When the protonation takes place, there will be 4 groups attached to nitrogen instead of 3 alkyl groups in case of amine. So the conjugate acid will be less stable. That is why the decreased basicity. I hope I have answered your question. Next slide. Next is reduction of nitriles. Now important thing here is nitriles you can reduce to amines having same number of carbons. You can use variety of reducing agent. You can use H2 nickel. You can use sodium amalgam ethanol, that is called Mendius reduction. You can use sodium in ethanol, and you can use lithium aluminium hydride. Any of these reducing agents. Let me write it for you. As I said, sodium amalgam ethanol is called the Mendius reduction, or you can use LaH. The product is the corresponding primary amine. Nitriles. In case of isonitriles, however, what happens here is that you can do the reduction with H2 nickel catalyst or with LaH, but the product obtained will always be a secondary amine, where one of the groups attached to nitrogen will always be methyl. Okay? So isonitrile reduction can be used to prepare N-methylamines. एक पीछे वाली slide में. Amides here, if you see, Amides can be reduced to corresponding amines by reduction with LAH in ether. That is the only reducing agent you can use, LAH ether, to convert amides to amines. Next slide. Next is reduction of nitro compound. Now if you have a nitro compound, again variety of reducing agents you can use, H2 nickel, tin HCl, aliphatic and aromatic both, iron HCl or LAH. You can use any of these for reduction of aliphatic nitro compounds to aliphatic amines. Also for aromatic compound, important thing you have to remember is LAH you can use only for aliphatic nitro compounds. Aromatic nitro compounds में LAH reduction करने से the product obtained is azobenzene. If I take aniline, I cannot reduce it with nitrobenzene, cannot reduce it with LAH to aniline. The product obtained will be azobenzene. So I can use any of these reducing agents, but not LAH, to obtain aniline from nitrobenzene. Is that okay? Next slide. Next is reduction of oximes. Now oxime reduction offers a means of converting a carbonyl compound to the corresponding amine. If you have a carbonyl compound and you want to convert it into an amine, this can be one of the routes. How? You can see on the slide, oxime, you can reduce it with lithium aluminium hydride or with sodium in ethanol, and the corresponding product is amine. You replace C double bond NOH by CH NH2. Now what I was trying to tell you was that this offers a means of indirectly converting a carbonyl compound into an amine. See, if you have a carbonyl compound, you react it with hydroxylamine, what is the product? The product is an oxime, and that you reduce with LAH. So indirectly you have been able to convert a carbonyl compound into an amine having same number of carbons. Is that okay? Next slide. Next is the Gabriel Thalamide synthesis. Gabriel Thalamide synthesis is the best synthesis to prepare aliphatic primary amines or primary aryl alkyl amines, but you cannot prepare aromatic amines by this reaction. That you have to remember. Okay? Primary aliphatic amines or primary aryl alkyl amines, not aromatic amines by this reaction. We will try to understand that why. If you see the reaction here, what is happening here is that you start with potassium thalamide, reacted with KOH, thalamide being converted into potassium thalamide here. Then you reacted with alkyl halide. This is nothing but an SN2 reaction. Okay? So what will happen? You will get N-alkyl derivative being formed, and this N-alkyl thalamide on hydrolysis with alkali will give you corresponding amine. So this R X is replaced by NH2. So whatever alkyl halide you start, just replace that X by NH2. That is the reaction in Gabriel Thalamide synthesis. Okay? But as I said, not to be used for aromatic amines, because aromatic amines do not, aromatic alkyl halides do not undergo an SN2 reaction. Do aryl halides undergo SN2 reaction? Aryl halides do not show SN2 reaction, therefore you cannot use fluorobenzene and get aniline by this reaction. Is that okay? That you have to remember. Next slide. Next is reductive amination of aldehyde ketone. Now when we learned that reaction for oxime, I said it is an indirect method of conversion of carbonyl compounds to amines. Okay? Reductive amination is a direct method to convert carbonyl compounds to corresponding amines. So how do you do this reaction? take a carbonyl compound, okay, react it with ammonia or primary amine or secondary amine. Important thing about this reaction is you can use it to prepare primary amines, secondary amines and tertiary amine. All the three kind of amines can be prepared. If you use ammonia, you will get primary amine as the product. You use primary amine, you will get secondary amine as the product. And if you get secondary amine, you will get tertiary amine as the product. Is that okay? I will just write one reaction and explain how this reaction is taking place. The reaction takes place in presence of a reducing agent. Either you can use H2 nickel or you can use sodium cyanoborohydride, one of these reducing agents, to convert C double bond O again into CHNH2. As I said, carbonyl compounds to corresponding amines. Let me tell you one example. I have taken example of ammonia here. I will give you an example of a reaction when I use primary amine. Okay? H2 nickel, or you can use sodium cyanoborohydride, one of these reducing agents. So what is the product obtained? The first product obtained is an amine which under reducing medium so when you start with a primary amine, what is the product obtained? What kind of amine is this? There are two hydrogens replaced on nitrogen, so it is a secondary amine, correct? So when I start with a primary amine, I have got secondary amine. When I start with ammonia, I have got a primary amine. Likewise, if I start with secondary amine, I will get a tertiary amine as the product. Is that okay? So all the three kind of amines can be prepared by this reaction. Next slide. Next is Hofmann degradation. Now Hofmann degradation offers a conventional step down reaction where you can convert not only amides to amine having one carbon less, but it offers an indirect method of conversion of carboxylic acids also to amines having one carbon less. Let us understand this reaction. So if you have an amide reacted with bromine in KOH, you will take this alkyl group and attach an NH2 to this, and that will be the product. Forget about this group, okay? Take the alkyl portion or the aryl portion and attach a NH2 group. That is the product. So there were 3 carbon chain earlier, now you've got a 2 carbon amine. Step down by 1. I said indirect method to convert carboxylic acids to amine having 1 carbon less. You know, this is propionic acid. Okay? If I react it with SOCl2, what will be the compound obtained? What will I get? Propionic acid with thionyl chloride will give me? Correct? Acid chloride. Now this, if I react with ammonia, will give me an amide. So indirectly what I have done, I have converted a carboxylic acid to an amine having 1 carbon less. So either an amide or a carboxylic acid can be converted into amine having 1 carbon less. Correct? Next slide. Schmidt reaction. Schmidt reaction is an example where you can directly convert a carboxylic acid to an amine having 1 carbon less. You can see here, if you start with a carboxylic acid, react with hydrozoic acid in sulfuric acid, you get amine. So, for example, if you have Again concentrate on this R, forget about this COH and add NH2. That is the product you get. Okay? This is Schmidt reaction. Direct conversion of propionic acid to ethylamine. This is indirect conversion of propionic acid to ethylamine. Okay? Now we have studied so many reactions. Let us try to summarize these reactions that we have studied. Now if you see here, if I start with an chloroalkane, alkyl halide, if I react with sodium azide, I will get alkyl azide, correct? That on reduction will give me an amine having same number of carbons. If I take alkyl halide and react it with potassium cyanide, I will get alkyl cyanide, correct? One carbon increase, step up reaction. Alkyl cyanide you reduce, you can get a amine having one carbon more. You understand what I am trying to say? See, you have an alkyl chloride reacted with potassium azide, you get RN3, reduce it, you get RNH2, correct? Alkyl halide to an amine having same number of carbon. Same alkyl halide you react with potassium cyanide, RCN, reduce it with LAH, you will get an amine having one carbon more. Okay? Same alkyl halide, step up, retention of number of carbons here. This if you hydrolyze, you will get RCOOH, correct? React with hydrozoic acid, step down, convert it into amide, Hoffman bromamide, step down. If you reduce it with LAH, retention of number of carbons. You can see how starting from a compound we have converted into a variety of products with retention or with increase in number of carbons or with decrease in number of carbons. Okay? That is how you should try to correlate the reactions, and this will be helpful to you when you do the conversions, the questions that we will try to attempt. Is that okay? Next slide. Diazotization. Diazotization is one method to convert aromatic amines into diazonium salt. If you have an aromatic amine, you react it with nitrous acid. The nitrous acid is actually generated in C2 by reaction of sodium nitrite and mineral acid, which can be HCl or it can be H2SO4. Okay? And you get the corresponding diazonium salt, and this reaction is called the diazotization reaction. Okay? With this we have done all the methods of preparations of ammonia, nitrogen compounds, amines and the diazonium salts. We will go on to now their reactions. Next presentation. Next presentation. Chemical properties and reactions. So first we will do reactions of amines. Now reactions of amines we can categorize into three different categories. First is the reaction where it exhibits the basic character. Next will be reactions, these three reactions where it is showing the nucleophilic character as a nucleophile. And next will be some miscellaneous reactions and reactions due to the aromatic ring that we will do later. Okay. Next slide. Now because amines are basic, they dissolve in water to get ionized, they will also dissolve in acid. If they can take up a proton from water, they will easily take up a proton from acid. Okay? So if you dissolve it in HCl, you will get the corresponding salt being formed. So what makes amine soluble in acid? It is the formation of salt, which makes them soluble in water. If you want to recover the free base back, treat it with sodium hydroxide, you will get back the free base. Correct? Next slide. Now, like silver chloride or cupric chlorides, they are soluble in ammonia. They will also be soluble in primary amines because of the formation of these coordination complexes. So silver chloride is soluble in primary amine because of formation of this kind of similar coordination complex that you get in case of ammonia also. Okay? Similarly, cupric chloride will also be soluble in primary amine because of the formation of similar coordination complex. Is that okay? Next slide. Alkylation of amine, this we have done actually when we were doing the Hofmann ammonolysis reaction. We have seen how SN2 reaction we can convert a primary amine to a secondary amine to tertiary amine. Again, not a very good method because you get a mixture of amines in any case. Correct? Important thing you have to remember is this: exhaustive alkylation. Whenever you are reacting primary, secondary or tertiary amine with excess of alkyl halide, you convert them into quaternary salts. So conversion of primary, secondary or a tertiary amine to quaternary salt is what we call exhaustive alkylation. Importantly, for this reaction, you should start with primary alkyl halide, because if you start with a secondary alkyl halide, you will get a elimination reaction competing. Okay? So if you have a primary alkyl halide, your major product will be substitution reaction, but if you have a secondary alkyl halide, you will get elimination product also coming into play. Next slide. Acylation of amines. Now, if you have an amine and you replace, for example, ethylamine, you react it with acid chloride or acid anhydride. In either of the cases, what happens is the hydrogen is replaced by COR group. The COR group is called the acyl group and the reaction is called acylation reaction. Okay? So the product obtained here will be okay? This is an acyl group. So if I take R as CH3, what will happen? This compound will be called acetyl chloride. So the reaction will be called acetylation. Correct? And the product obtained will be N-acetyl derivative. Okay? The hydrogen being replaced by a CH3 CO group. Now important thing that you have to remember here is, if I take alkyl halide, I have a poly substitution taking place. But when I react with acyl halide, there is no poly substitution taking place. The reason is, the moment I introduce this acyl group, the carbonyl group offers minus I. Okay? Because of which the nucleophilic character of this nitrogen is decreased. The lone pair will get delocalized like this. So the lone pair of electrons are no longer available on nitrogen. That is why poly substitution reaction will not take place. The reaction will stop at the monoacylation stage. Okay? Now, in case of acetyl chloride, what will be the byproduct obtained? What will be the byproduct obtained? The byproduct obtained will be HCl. Okay? So for many compounds, when you do the acetylation reaction, the acetylation reaction is done in place of organic bases like pyridine. What is the role of pyridine? The role of pyridine is to remove this HCl and to facilitate the reaction in the forward direction. Pyridine will take up this HCl and remove it. The reaction goes in the forward direction smoothly. Correct? But if instead of methyl I have a benzene ring here, this will be called benzoyl chloride. This is acetyl chloride, this is benzoyl chloride. Then this reaction takes place in presence of aqueous sodium hydroxide. The role is same, to remove HCl only. Okay. So you will get the corresponding N-benzoyl derivative. Here you got N-acetyl derivative, here you have got N-benzoyl derivative. So any reaction of compounds having active hydrogen, like you have amines, you have phenols and you have alcohols. When you react them with benzoyl chloride in aqueous NaOH, the reaction is a benzoylation reaction. It is commonly known as Schotten-Baumann reaction. Okay, benzoylation of amines, phenols or alcohols, that is called Schotten-Baumann reaction when it takes place in presence of sodium hydroxide. Next slide. The acylation reaction, like with acid chloride, can also take place with sulfonyl chloride. So if we have benzene sulfonyl chloride, the same reaction will take place. The hydrogen will be replaced by benzene sulfonyl group. H from here, Cl from here, lost, and you get the corresponding product being formed. So it will be so these compounds are called sulfonamides. They are called sulfonamides. Now, important thing you have to remember here is, unlike these acetyl derivatives, because of the strong minus I effect of sulfonyl group, this hydrogen is acidic. So sulfonamides are acidic in nature. So if I dissolve it in sodium hydroxide, it will dissolve because of formation of the corresponding sodium salt. This proton will be abstracted and you will get the corresponding sodium salt being formed. Now this reaction is actually basis of distinction and separation of primary, secondary and tertiary amine, and this reaction is called Heisenberg's test. Let us see how you can use Heisenberg's test to distinguish between primary, secondary and tertiary amines. Okay? Written? This primary, secondary or tertiary aliphatic amines, primary, secondary and tertiary aromatic amines. Okay. If you react with benzene sulfonyl chloride, आजकल what is done is benzene sulfonyl chloride is being replaced by, this is called para-toluene sulfonyl chloride. ठीक है? So what will happen? One H and Cl goes and you get the corresponding sulfonamide being formed. ठीक है? There is one hydrogen still remaining. ठीक है? If I put this in sodium hydroxide or potassium hydroxide, this hydrogen will be removed to form the corresponding salt, and this sulfonamide will become soluble in sodium hydroxide. This is soluble. Correct? In case of secondary amine, what will happen if you do the same reaction? Do you have a replaceable hydrogen? Does your nitrogen have a replaceable hydrogen? This is the sulfonamide formed. Does the nitrogen have a replaceable hydrogen? No. No? So it will not be soluble in sodium hydroxide or potassium hydroxide, insoluble. Correct? And tertiary amine, it doesn't have a single hydrogen attached to nitrogen. So what happens? It cannot lose this HCl. So there is no reaction. And if I add KOH, there will be no change. Correct? The similar reaction can take place with aromatic amines also. Now, how to distinguish them? Visually, how will you see? What you find is, in case of primary amine, when you put KOH, it will become soluble. Correct? Because of formation of this salt. But if I put HCl, what will happen? It will again go back to this state and it will again precipitate. Put KOH, it becomes soluble. Add HCl, it will get precipitated again. ठीक है? In case of secondary amine, you put KOH, it is insoluble. You put HCl, will there be any change? No change. Correct? Tertiary amine, because nitrogen doesn't have a hydrogen, it does not react with para-toluene sulfonyl chloride, so it remains oily because of unreacted tertiary amine. But KOH, again no change. Correct? But what will happen when I put HCl? Anything will happen when I put HCl? It will become soluble because tertiary amine will form the salt and HCl डालने से it becomes soluble. So tertiary amine will become soluble when you put HCl, primary amine will precipitate when you put HCl, and secondary amine there will be no change. That is how you can distinguish between primary, secondary, tertiary amine using the Hinsberg's test. Is that okay? Any doubt? Next slide. Next is formation of Schiff's bases. Primary amines, only primary amines, not secondary, not tertiary, combine with aldehydes and ketones, again because of their nucleophilic character. Presence of two hydrogens is required here, okay, which is only present in case of primary amine, not in case of secondary or tertiary amine. They will form compounds which are called imines or Schiff's bases. They are highly colored compounds. What is happening here is That can be primary aliphatic amine or aromatic amine also. So if I take propanone, okay, and if I react it with aniline, what will happen? H2O. There is a loss of water molecule and you will get and these compounds are called Schiff's bases. Okay. Reaction only for primary amines, aliphatic or aromatic. Correct? Next slide. Reaction with nitrous acid. Again, reaction with nitrous acid is used as a distinction between primary, secondary and tertiary amines. Let us see whether aliphatic or aromatic, both. We will see how. Now, in case of primary aliphatic amine, what happens here is when you react with nitrous acid, it will form the corresponding diazonium cation. Okay? But aliphatic diazonium salts are not stable. Okay? And it will immediately lose a molecule of nitrogen to undergo an elimination or substitution reaction. Now, in the reaction medium, you have water. Okay? So, water can attack here. You can get the corresponding alcohol being formed. How did you get nitrous acid? NaNO2 HCl, right? So you have chloride ion. So Cl minus is there. So Cl minus can attack here and you can get alkyl halide. Now, also one more possibility. This is the simplest amine. Instead of methylamine, if I take ethylamine, there is one more possibility, and that possibility is loss of a proton to form alkene. So primary aliphatic amines on reaction with nitrous acid, they will give you a mixture of alkene and two substitution products, corresponding alcohol and an alkyl halide. Important thing you have to remember is this: primary amine with nitrous acid give you alcohols. This reaction is used in estimation of amino acids and proteins in the industry also. The reaction is called Vance-like method. Okay? Let us come to secondary amines. What will happen in case of secondary amines? In case of secondary amines, you have N-nitroso derivative being formed. What will happen? NO group will get attached to nitrogen and it precipitates as yellow oil. The medium is acidic, NaNO2 HCl, acidic medium hai, correct? Because this is not basic, it precipitates in the form of yellow oil. Okay? Tertiary amines, when you react with nitrous acid, they will dissolve because of the formation of, you have a simple acid base reaction taking place and you have this salt being formed. Okay? So primary amine you get alcohol, secondary amine you will get yellow oil because of formation of N-nitroso, tertiary amines dissolve due to formation of salt. Let us see aromatic amines, what happens. If I start with aniline, I take N-methylaniline and I take NN-dimethylaniline. This reaction takes place at 0 to 5 degrees centigrade, beyond which the diazonium salts are not stable. You will get what? Benzene diazonium chloride being formed. How can you confirm the presence of benzene diazonium chloride? You put phenol at a pH of 9 to 10 and you get a bright orange red color dye being formed. So formation para-hydroxyazobenzene, that is the dye which is formed, and that confirms that you have a primary aromatic amine. Correct? In case of a secondary aromatic amine, the reaction will be same as in case of aliphatic amine. You get N-nitroso compound being formed. Again yellow oil. Okay? This can be identified by, I don't know if you have heard this name, Lieberman nitrosoamine test. If you take this yellow oil, put a drop of phenol and sulfuric acid, you heat it, you get green coloration, add sodium hydroxide, you get a blue coloration, dilute with water, you get a red coloration. This is called Lieberman nitrosoamine test. A typical test for secondary aliphatic or aromatic amines. Okay? They can be identified by this colored reaction. Finally, when you come to tertiary aromatic amines, what happens is NO plus, which is generated in the reaction, acts as an electrophile and you get a green colored salt being formed because of an electrophilic substitution reaction taking place. So you get para-nitroso NN-dimethyl-aniline, which is a green colored salt which gets precipitated. Is that okay? That is how you use nitrous acid to distinguish primary, secondary and tertiary aromatic amines. Okay? The next slide. We have discussed this already. Next slide. Again we have discussed. Next slide. Next slide, next slide. Next slide, we have done this. Next slide. Next slide. The next reaction is Hofmann elimination. Now quaternary ammonium salts, if you react with moist silver hydroxide, they are converted into quaternary ammonium hydroxides, which at heating at 300 degrees centigrade undergo an elimination reaction which is called Hofmann elimination. We will try to understand what is this Hofmann elimination reaction. So reaction given by quaternary ammonium salts. You have this quaternary ammonium salt, react it with moist silver oxide, you get the corresponding hydroxide being formed. So this acts as a base, OH minus is the base. When you heat this at 300 degrees centigrade, it undergoes what we call a beta elimination. Beta elimination, you locate the types of beta hydrogens that are present. This is alpha carbon, this is beta carbon. Okay? Again alpha, beta carbon. So you have two types of beta carbons available. Beta elimination is loss of hydrogen from carbon which is least substituted. So you have to locate the beta carbon which is least substituted. Means if you see this beta carbon, there is no other substituent on this. Okay, there is no other carbon here. But if you see this beta carbon here, there is another methyl group here. So which is more substituted? This carbon or this carbon? Which is more substituted? This carbon has 3 hydrogens and only one alkyl group attached to it. This carbon has 2 alkyl groups attached to it. Which is more substituted? This one. Correct now? Because this has 2 alkyl groups and 2 hydrogens. This has 1 alkyl group and 3 hydrogens. So this is less substituted. So hydrogen will be lost from a carbon which is least substituted. Okay? So we say the most acidic proton will be lost, because here what happens is this alkyl group will offer plus I. So the acidity of this hydrogen attached to this beta carbon will be less than acidity of this hydrogen attached to this carbon. So what will happen? You get H here, this OH minus will take up this proton. That is the least substituted carbon of the two, है ना, or the most acidic proton, correct? Will take up this proton. You will have elimination taking place like this, and you will get a tertiary amine plus an alkene. So alkene formed will be the one which is least substituted. Okay? Next slide. This we have explained. Next slide. Next slide. Next is oxidation of amines. Now amines can be oxidized by using variety of oxidizing agent. That can be potassium permanganate, it can be Carrot's acid, it can be hydrogen peroxide. Depending upon nature of oxidizing agent used, different amines will give you different products. Okay, I will write one example for each one of them. This is a primary amine having a tertiary alkyl group attached to it. When you oxidize such amines with KMnO4, the oxidation product is the corresponding nitro compound. If you have a secondary amine, oxidize it with KMnO4, you get tetraalkyl hydrazine being formed as the product. And secondary amine, if you oxidize with Carrot's acid, the product is the corresponding hydroxylamine. Okay? And if you have a tertiary amine, it can be oxidized with Carrot's acid, H2SO5, or with hydrogen peroxide, and the product obtained is an N-oxide. If you know, the amines when pure, they are normally colorless. They are stored in dark amber colored bottles. That is to prevent their oxidation, because light catalyzes their oxidation. Okay? On oxidation, they acquire color, and that is because of the presence of the oxidation product, that a sample of an amine becomes colored. If there is no oxidation taking place, they are normally colorless. Okay? Next. Next slide. We have discussed this. Next slide. So next is reaction with phosgene gas. If you see here, aniline, when you react with phosgene gas, what will happen is aliphatic amines give you substituted ureas, but aromatic amines give you the corresponding isocyanates. If you have an aliphatic amine, what will you get? One HCl lost from here and one more alkyl amine. Combining with this, another HCl lost from here, and you will get dialkyl urea. One amine here, HCl lost, another molecule amine here, one mole HCl lost. You get dialkyl urea. Secondary amine, correspondingly similar reaction it will show. But if you have an aromatic amine like aniline, when you react it with phosgene gas, the first product obtained is which on heating loses HCl and it forms phenyl isocyanate. Okay, that is the product. Next slide please. The next reaction is the Hoffman mustard oil reaction. If you see the aliphatic amines, when you react with carbon disulfide, they will first form dithionic acid, and when you heat with mercury chloride, you will get alkyl isothiocyanate, which gives you that smell of mustard oil, and a black precipitate because of formation of mercuric sulfide. Okay. Similarly, in case of aromatic amines also, you will get this corresponding isocyanate being formed, which will give you this mustard oil smell. That is why this reaction is called mustard oil reaction. Next slide. We have done this. This reaction is important. We have not done this. If you have to differentiate a primary amine, whether that is aliphatic or aromatic, from a secondary or a tertiary amine, the best reaction is carbylamine test. What is carbylamine test? You take a primary amine, whether it is aliphatic or aromatic, reacted with chloroform in presence of alcoholic KOH, and you get the corresponding isocyanide or the carbylamine, which gives you that offensive odor. Okay, so that reaction will take place only for primary amine, aliphatic or aromatic. Okay, so that can be used to distinguish a primary amine from a non-primary amine. Correct? Carbylamine reaction. Nitrous acid we have already done. Hinsberg test also we have discussed the chemistry in detail. Okay, we have done this. Next slide. Next slide. Back. Piche. Next is the reactions of aromatic amines. We will see the ring substitution taking place. Now you can very well understand that amino group is ring activating, so it will be orthopara directing in an electrophilic substitution reaction. But what happens in case of aromatic amines is that NH2 is the strongest ring activating group. So what happens is you have a poly substitution taking place. If I do the reaction of aniline with bromine in acetic acid, my product, or bromine in water, my product obtained will be if I take bromine water, my product obtained will be 2,4,6-tribromoaniline. So you have a poly substitution taking place because ring is highly activated for an electrophilic substitution reaction. So if I have to do controlled reaction, what I have to do is first I have to reduce the electron donor ability of this nitrogen. How can I do that? I can convert it into a corresponding acetyl derivative. We have learned how we can do that, acetyl chloride or acetic anhydride. You can, this compound is called what? It is called acetanilide. Correct? Now, the difference here is that acetanilide, nitrogen has a carbonyl group attached to it. So what will happen? This lone pair of electrons will get delocalized onto oxygen. So acetanilide, nitrogen is less ring activating than in case of aniline. So now you can do controlled electrophilic substitution reactions. And you know already that when you have a donor group, the incoming electrophile will come ortho and para. But because you have a bulky group here, it is a big group, acetamido group is a bulky group, so para product will be a major product. You understand what I am saying? So if I do bromination of acetanilide now, you have seen bromine water, you get 2,4,6-tribromoaniline. I convert this into acetanilide, reacted with bromine in acetic acid. What will I get? A mixture of ortho and para substituted product, where major product will be what? What will be my major product? The para substituted will be major product because of steric factor, as I said. Okay? Now you can hydrolyze this. So it is an indirect method of bromination of aniline. You can do selective bromination. You will get a mixture of ortho and para bromoaniline. Correct? Where para of course will be the major product. Right? One more thing I want to tell you here. Any reaction of aniline which is done in acidic medium, when you are doing electrophilic substitution reaction in acidic medium, because aniline is a base, it will combine with acid to form. What will it form with acid? Anilinium cation. So in acidic medium it becomes ring deactivating. So any electrophilic substitution reaction which is taking place in the acidic medium, you can expect lot of meta substituent as the product. Ring deactivating groups are meta directing in an electrophilic substitution reaction, correct? Ring deactivating group like nitro group, like nitrile group, they are meta directing in electrophilic substitution reaction. So a major product obtained in this case also will be a meta substituent because of formation of anilinium ion. Okay, let us take the examples now. Next slide please. So resonance structures of aniline we have already learned when we were doing basicity. Okay, you have learned. Next slide. So this reaction we have just done. How you can do selective bromination, and if you do hydrolysis here, you can get ortho and para substituted aniline. Next reaction. Nitration. Now if you do direct nitration, nitric acid and sulfuric acid is a nitrating agent that you use, but please remember concentrated nitric acid, besides being a nitrating agent, it is a very good oxidizing agent. Now because the benzene ring is highly activated in case of aniline, when you do nitration directly, it will lead to complete oxidation of the ring and you will get aniline black being formed as the product. Is that okay? But if you do controlled nitration at a temperature of about 288 K, you can get a mixture of para-nitroaniline and ये क्यों चल गया? हेलो ये ठीक है. I told you what will happen in presence of nitric acid. You will have anilinium ion being formed. The moment anilinium ion is formed, it will be meta directing. So one of the product obtained will be meta nitroaniline. So that is the reason here you have got 1:1 mixture of para nitroaniline and meta nitroaniline being formed on nitration of aniline. Correct? Next slide. Sulfonation reaction, again because of protonation you will get anilinium hydrogen sulfate being formed, ring deactivating. So sulfonation of aniline takes place only under drastic conditions, 455 to 475 K to give you anthranylic acid. This is para-amino benzene sulfonic acid. Okay. Next. Aryl amines do not undergo Friedel-Crafts reaction because aniline NH2 group is a Lewis base and Friedel-Crafts reaction uses Lewis acid AlCl3 as a catalyst. So they will combine together to form a complex, so which is highly ring deactivating. What will be that complex? This complex which is formed is highly ring deactivating. It prevents Friedel-Crafts reaction from taking place on aniline. So if you have to do Friedel-Crafts acylation reaction, what you do is, again first convert aniline to acetanilide, okay, and then you do the reaction with benzoyl chloride in ACl3 and you can do the benzoylation reaction here. Can you see here? So directly with aniline not possible because of the formation of the complex I have shown you here. Indirectly you can convert to acetanilide and then do the Fiedel-Crafts acylation reaction. Please remember there will be no ortho product formed here because of steric factor. So the major product formed will be para-benzoyl derivative, okay, and that you can hydrolyze and get back this NH2 group here. So indirect benzoylation of aniline can be carried out like this, okay. Next slide. The last of this is reactions of diazonium salts. Now diazonium salts offer a wide variety of reactions where you can convert an aromatic ring to chlorobenzene, bromobenzene, iodobenzene. You can introduce nitrile group, you can get phenol, you can get fluorobenzene, you can get nitrobenzene. So you can see here importance here is this reaction. Directly you cannot prepare alkyl fluorides or alkyl iodides, okay. So diazonium salt offers an indirect method of preparation of alkyl iodides and alkyl fluorides, number one, and also you cannot introduce this nitrile group, CN group directly onto the benzene ring. Again, diazonium salt offers a method of introducing a CN group, the nitrile group directly onto the benzene ring, okay. We will see the individual reactions. There are two types of reactions of diazonium salt that we will do. First, where the N2 will be replaced, and second set of reaction where nitrogen will be retained, okay. So first set of reaction where the nitrogen is replaced, okay. The first of those is conversion of a benzene ring to aryl halides. Two type of reactions can be done. First is the Sandmeyer reaction and the second one is the Gutterman reaction, okay. So if you have benzene diazonium chloride, you can react it with CuCl HCl, CuBr HBr, or you can react it with CuCN KCN and get the corresponding chlorobenzene here. You will get bromobenzene here and here you will get benzonitrile. This reaction is called Sandmeyer reaction. Okay. Alternatively, you can do reaction with copper in HCl or copper in HBr. This reaction will be called a Gutterman reaction and you can get the corresponding aryl halides being formed. Is that okay? So this is how you convert a diazonium salt into an aryl halide, or you can convert it into a aryl nitrile. If you have to prepare an iodide, you can directly react it with Ki or NaI. You don't need to use copper catalyst. You will get iodobenzene, okay. And if you have to convert it into fluorobenzene, then what you do is you convert it into you react it with to convert it into fluorobenzene, you need to convert it into benzene diazonium tetrafluoroborate, which on warming will give you fluorobenzene. This reaction is called Schimann reaction, correct? So this we have learned how to convert into aryl halides of different types and how to prepare benzonitrile. from diazonium salts. Next slide. Next slide. So we have done this. Next slide. If you have to convert benzene diazonium chloride into benzene, you use a reducing agent. That reducing agent can be either H3PO2, or you can use sodium borohydride, or you can use ethanol. One of these you use and the product obtained will be benzene. So N2 being replaced by hydrogen. Okay. If you have to replace it by OH group, form phenol, take diazonium chloride, boil it with water, you get phenol. Okay. So we have seen how aryl halides are formed, how benzene is formed, how phenol is formed, how benzonitrile can be formed. Okay. Next slide. Nitro compound. If you have to prepare nitro compound, then what you have to do is you prepare first benzene diazonium tetrafluoroborate and react it with sodium nitrite in copper. So you get nitrobenzene. Okay. This benzene diazonium tetrafluoroborate reacted with NaNO2 copper, you get nitrobenzene. Okay. Next slide. The last category is reactions which involve retention of nitrogen. These are coupling reactions of diazonium salts. Diazonium salts coupling reaction is formation of a carbon-carbon bond. Okay. Diazonium salts undergo coupling reactions with phenol in the basic medium pH 9 to 10, and they undergo coupling reaction with amines in the acidic medium at a pH around 4 to 5. That you have to remember. With phenols you require a basic pH of 9 to 10. With amines you require an acidic pH of 4 to 5. Next slide. See here. This is nothing but an electrophilic substitution reaction taking place. So if you have benzene diazonium chloride, pH 9 to 10, combine it with phenol, the coupling reaction will take place at para position to the phenol here. So what will happen? Hydrogen is here, HCl lost, and you will get the corresponding diazo compound. This comes as an orange red colored dye. Okay. Now what you have to remember here is why you require alkaline pH. What happens is in the basic medium phenol will be converted into phenoxide ion. Now phenoxide ion is a stronger nucleophile because what happens is oxygen acquires a negative charge. So the nucleophilic character is increasing. So the reaction is facilitated. That is why coupling with phenols will take place in the basic medium. Okay? And if you have to couple with amines, NN dimethyl aniline, the reaction takes place in the acidic medium of 4 to 5, and you get again the coupling taking place at para position if it is free. If para position is not free, only then it will go to ortho position. Please remember that. Okay? Aniline, if you have to do, let me answer this question from this caller. If you have to do a Fiedel-Crafts alkylation reaction, you have to react with alkyl halide in AlCl3. Now I have already said that aniline is a Lewis base. This Lewis base will combine with Lewis acid and it will form because of formation of this salt, it is highly ring deactivating. So an electrophilic substitution reaction with alkyl halide cannot take place. ठीक है, वापस पहुंच जाए इस पे, ठीक है. फिनॉल्स के साथ बेसिक मीडियम and with amines in the acidic medium to form the corresponding colored dye. All right. Now we come to questions. 1 minute rest. Any doubts? I'm also tired. Very big chapter. Okay, let us start with first question. You see the first question? What is the first question? It says, if you can't see it properly, let me write it on the board for you. ये reaction है. You have to predict the product. What is the first reaction? The first reaction is a Hofmann bromamide reaction, correct? So if you have a Hofmann bromamide reaction, what will happen? CONH2 will be converted into amine. ठीक? Now when you heat it, what will happen? You will have cyclization taking place. So where is your product? Correct? That will be the product that you will get. ठीक है? ठीक है? Next slide. Next slide. Let us see this question. Aniline on reaction with COCl2 followed by heating. What is this reaction? Reaction with phosgene gas. And what is the product? Alkyl isocyanate. Phenyl isocyanate. Correct? So the correct option will be B. Right? The third reaction is what is this reaction? What is this reaction? Nitration. Where will the nitration take place? There are two benzene rings. Which ring will get nitrated and where? That is the question. Which ring is more active for this is an electrophilic substitution reaction, correct? Electrophilic substitution, which ring is more active for electrophilic substitution? This ring or this ring? Why this ring? Because it is attached to nitrogen. Though nitrogen has an acyl group attached to it, but still it is ring deactivating. Here you have a CO, carbonyl group attached to it, which is ring deactivating. So this ring is less active for an electrophilic substitution. Okay. This ring, now where? Para position, because ortho is sterically hindered, so the reaction will go at para position. That should be the position. Which is the product here? Number C, correct? That is option C, right? Next slide. Now it will be better. Out of these four compounds, which compound will form a colored dye with NaNO2HCl? What kind of amines form colored dye? with sodium nitrite HCl, what kind of amines will form di? This is a tertiary amine. Please see, this is a tertiary amine, this is a secondary amine. This is an aryl alkyl amine and this is a primary amine. So this reaction is characteristic of what kind of amine? Coupling reaction hai ye. This is a coupling reaction. What amine show coupling reaction? Aniline. Only aniline will show coupling reaction. Primary amine. Diazonium salt कौन सी amines बनाएंगी? Diazonium salts will be formed only by primary aromatic amine. This is a primary aliphatic amine if you see here. This is a primary aliphatic amine. So diazonium salt it will not show coupling reaction. Only a primary aromatic amine this will show coupling reaction. ठीक है? Next question. You have this compound para-nitrofluorobenzene. You reacted with NN dimethyl number 1, followed by reaction with tin HCl, NaNO2 HCl and H2 nickel. See the reaction. First write what will happen when you reacted with NN dimethyl. Can you say? What will be the reaction here? This is a nucleophilic substitution reaction, activated nucleophilic substitution reaction because you have an electron withdrawing group attached here. Okay? So the product obtained will be correct? Now, when you react with iron HCl, what will happen? This is a reducing agent. Nitrobenzene will be reduced to with tin HCl. We have done iron HCl, tin HCl. It gives what? Nitrobenzene will be reduced to aniline, NH2. Correct? So first you get NH2 here. Then is NaNO2 HCl. What is this? Diazotization reaction. So what will happen? You will get N2 plus Cl minus, correct? And then reaction with H2 nickel. Now diazonium chlorides, when you reduce with H2 nickel, they are reduced to hydrazines. First and the final product obtained is NH2. Okay? So what is your correct answer? Option A, correct? Next question. You have to predict the product in this reaction. देखो, toluene on nitration, what will be the product? लिखो फटाफट. Please write down. What is the product? Where will the nitro group go? The major product will be para, because of steric factor. Next is tin HCl. So what will happen when you react with tin HCl? Nitro will be reduced to NH2. And then diazotization and then CuCl HCl. So what is the final product? What is that reaction? Okay, diazotization to diazonium salt, and then CuCl HCl. What is this reaction? Sandmeyer's reaction. Huh? So you will get this. Correct? Huh? Correct? Next slide. Let's do some questions on basicity first. आगे चलते हैं, पहले basicity questions कर लेते हैं. Pick out the most basic compound in the following. Can you say which will be most basic? 1, 2, 3, 4. Which is most basic? What is this compound? If you remember, I told you this is piperidine. pKb value around 2.88. Nitrogen is sp3 hybridized. ठीक है? Plus you have 2 alkyl groups addition. Plus I effect. Strongest base will be this. Here there is an oxygen attached to the ring which offers minus I effect. So if you compare these two, this will be a stronger base. ठीक है? Here nitrogen has a lone pair of electron. This compound, the lone pair gets delocalized like this because of aromatization. So what happens is that nitrogen will acquire a positive charge. Because of positive charge, basic character will be less, and of course this will be least basic. ठीक है? So this will be the most basic compound amongst the 4. Next slide. Aniline is a question number 11, please. If you see, aniline is a weaker base than cyclohexylamine. This you can answer easily. This is very easy. Aliphatic amine, aromatic amine, resonance है, sp2 hybridized carbon है, decreased stability of anilinium ion है. All the 3 factors coming into play here. None of those factors come into play here. So this will be more basic. Correct? Okay. Next is, how will you convert acetaldehyde? Question number 13, please. Question number 13, you have to convert acetaldehyde to ethylamine. Let us write the structure. See please, what you have to pinpoint here is number of carbons is remaining same. ठीक है? How do you get amines? You can convert this into oxidation. You get acetic acid. Correct? What will happen? If you combine it with acetyl chloride and then react it with ammonia, what will happen? You will get amide. Correct? And that amide you can reduce with, क्योंकि same number of carbons हैं, you reduce with LAH. अगर reduce number of carbons होते, then you use Hoffman bromamide. ठीक है? That will reduce the number of carbons. Correct? Yes? Okay. Next slide. We have some more very interesting basicity questions which I wanted to do. Okay. पहले ये कर लेते. Question number 15, please. Let us see. Write the structure of ethanamine. Quickly, let us do. We will do 2 of them. How will you do? It is easy है. Directly you can do. How? Azide. Same number of carbons है. Correct? Next is methyl cyanide. Methyl cyanide is? So this is also easy. You can do directly. Same number of carbons. So you have to only do what? Reduction. LAH. You do reduction, you get directly. Correct? ठीक है? Next slide. Let us do question number 20. This is an interesting question. Which is more acidic and why? Anilinium ion and parafluoroanilinium cation. Which will be more acidic? Fluorine offers what? What type of electronic effect it offers? Halogens offer minus I. Because of minus I, what will happen is the positive charge on this nitrogen will increase. So the acidic character will increase. So the acidity will be correct? Next slide. We will do question number 23 first. Correct order of basicity for this. This will explain many things for you. This compound is this. Can you see here? This compound is called acetamidine. Now, when bases do what? Take proton. When it gets protonated, it will form this species. Okay? Now, this species is stabilized by resonance. You can see similar canonical forms. So the conjugate acid here will be highly stable. Because of the high stability of conjugate acid, this will be most basic. Number 1. In spite of the fact that nitrogen here is sp2 hybridized, it will be most basic because of resonance stabilization of the corresponding acid. Then you know secondary amine is more basic than primary amine. Secondary amine, then primary amine, and this is an amide. Now amides are not basic at all. Why? Because carbonyl group, the electron pair on nitrogen gets delocalized like this. So this will be 4. Understand? Any doubt? Now we can take question number 22. Which of the following reactions will not give primary amine? Please see. Primary amine. If you remember my statement, I told you, you should be able to tell me. What is this reaction? Hoffman bromamide reaction. Product is a primary amine? Correct. Nitrile on reduction with LAH, product is a primary amine. What happens when you reduce isocyanides? What is the product obtained? I told you it is used to prepare what? N-methylamines. What are N-methylamines? Secondary amines. So this reaction is the correct answer. C will not give you a primary amine. Fourth case, amide. Also on reduction give you primary amine. Okay? Only isonitriles on reduction will give you a secondary amine. Correct? Any doubt? Next slide. Next slide. Let us take this question number 26. A compound, aromatic compound on reaction with ammonia and heating forms B, which on reaction with bromine on KOH forms C. So what should be B? Bromine KOH is what reaction? Hofmann-bromamide reaction. So Hofmann-bromamide reaction takes place on what? Amides. So B should be an amide. Now B is formed by reaction of ammonia. Okay? So A should be what? What reacts with ammonia to form amide on heating? Carboxylic acid. Okay? So A should be a carboxylic acid. Correct? What will be A? It will be benzoic acid. When you combine with ammonia and heat, it will form amide. This, when you react with bromine KOH, will give you amine having one carbon less. So you will get aniline. So that will be your C. Correct? One last question we will take. Let us see. Next slide. This is a very good question. Which of the following compounds are chiral and resolvable? Please remember, I told you quaternary ammonium salts are chiral and resolvable. Tertiary amines are not resolvable even if they have all three different alkyl groups attached because of pyramidal inversion. Correct? So first one is a resolvable or not? C, the charge on nitrogen. It is about quaternary ammonium salt. So chiral and resolvable. Correct? What about second one? Nitrogen के ऊपर plus charge, is it there? No. So that means it is a tertiary amine. Chiral, is it resolvable? Pyramidal inversion. So not resolvable. Correct? Third one, again nitrogen carrying a positive charge. So resolvable? Correct? Fourth one, again nitrogen carrying a positive charge. So resolvable. What about last one? That is what is important. Not resolvable. It is chiral and resolvable. And the reason is this is the structure. Can you tell me why it is resolvable now? Why it is resolvable? It has a chiral center, carbon. Carbon is responsible for the optical activity of this compound. Is that okay? That's all.